Hello. In this video, we are going to talk about polar curves and areas. So, let's consider a polar curve r equals f of theta, where theta is between alpha and beta. Now, let us also roughly sketch this polar curve. So, let's say that this is theta equals alpha. This line here is theta equals beta. And let's assume that our curve r equals f of theta is this one. Now, we want to consider the area bounded by this polar curve and the lines theta equals alpha, theta equals beta. So let me mark that area. Now, the formula that helps us to calculate this area is the following. Integral from alpha to beta of 1 over 2 r squared d theta. Now, let me say a few words about how we obtain this formula, and for that I need to recall some simple facts about circles. So, let's take a circle with radius r. So, we all know that area of this circle with radius r is pi r squared. Okay, now let's consider a slice of this circle with an angle of theta. So, area of a slice with radius r and angle theta is 1 over 2 theta r squared. Now, using this observation or using these simple facts, we can see where this formula is coming from. Now, let me divide this region into small slices. Now, here I consider in red a slice with an angle d theta. Now, keeping the angle small gives us the advantage to consider both sides of this slice to be the same. So, let me assume that both sides of this slice is r. Then, the area of this red slice, using the observation in the next board, is 1 over 2 r squared d theta. Now, imagine that we have divided our blue region into many small red slices like this, and then we calculate the area of each red slice and then add them, and this will give us the area formula for the region bounded by a polar curve. In this exercise, we are going to find the area of the region bounded by the polar curve r equals 2 cosine theta, where theta is between negative pi over 4 and pi over 3. So for these kind of questions, it's highly recommended that you first sketch the polar curve. And to sketch the polar curve in this exercise, we are going to first convert it into Cartesian equations. So to do that, we multiply both sides by r first, then using the relations between polar coordinates and Cartesian coordinates, we substitute r squared by x squared plus y squared and r cosine by x. Then we rewrite this Cartesian equation as follows. From which we recognize that this polar curve is in fact a circle with radius 1 and center at 1, 0. Now we can sketch this polar curve. It's a circle with center 1, 0 and radius 1. So it's a circle whose center is shifted along the positive side of the x-axis by 1 unit. Then let us mark the range for theta on this picture. So here is theta equals negative pi over 4, and here is theta equals pi over 3. So we want to calculate this region. Now, our area formula says that this region, the area of this region, is equal to the integral from negative pi over 4 to pi over 3 of 1 over 2 r squared, which is 2 cosine theta squared d theta. Now, in the rest of the exercise, I'm going to evaluate this integral. First of all, we simplify the expression inside the integral. This is 2 cosine squared d theta. Now, to evaluate the integral of cosine squared, I need to use a trigonometric identity, and I substitute for 2 cosine squared, cosine 2 theta plus 1. We know how to integrate cosine 2 theta. It is sine 2 theta over 2. Integral of 1 is theta. Then we substitute our boundaries. If you substitute your boundaries in this formula, you are going to get square root of 3 plus 2 over 4 plus 7 pi over 12. Okay, now we are going to talk about area of a region between two polar curves. So let us consider these two polar curves. R1 equals f of theta and R2 equals g of theta, where theta is between again alpha and beta. So let us show in a picture how these two polar curves might look like. So I draw again the lines theta equals alpha and theta equals beta. So let's say that this one here is our curve R2 equals g of theta, and this one is R1 equals f of theta. So we are interested with this region, and the formula which will give us the area of this region is the following. Integral from alpha to beta 1 over 2 R2 squared minus R1 squared d theta. So let me mark this area in red. And we are going to use this formula to calculate area of the regions between two polar curves. In this exercise, we are going to find the area inside the polar curve r equals 2 sine theta and outside the polar curve r equals 1. So again, it is recommended that you sketch these polar curves and mark your area clearly. This will help you to set up your area integral correctly. So, to sketch these polar curves, let's start with 2 sine theta. I'm going to, again, convert it into Cartesian coordinates. Multiply both sides by r and substitute for r squared x squared plus y squared and for r sine theta y. Then we rewrite this and complete it into square. And we recognize that this equation represents a circle again with radius 1 and center 0, 1. So let us sketch that. So here is our circle with radius 1 and center 0, 1. Our second polar curve, r equals 1, we know that it is a circle with radius 1 and center at the origin. So let us sketch that as well. So here is r equals 2 sine theta, and here is r equals 1. So the region that we are talking about is inside r equals 2 sine theta and outside r equals 1. To be able to find the integral which calculates this red area, we need to find next the intersection point of these two polar curves. So let me first mark them on the picture. So we need these two values of theta. So it is intersection of the polar curves. So we set these two polar equations equal to each other and then solve it for theta. So we find the trigonometric equation sine theta equals 1 over 2. Now, from the picture, we observe that these two polar curves are intersecting once in the first quadrant and once in the second quadrant. So when you solve this trigonometric equation, you are looking for a solution in the first quadrant and a solution in the second quadrant. So these solutions are pi over 6 and 5 pi over 6. So let's copy those also on our picture. Okay, now that we have clearly sketched the region that we are trying to find its area, let's set up the integral which gives us this area. So it will be integral from pi over 6 to 5 pi over 6, 1 over 2, the outer polar curve, which is 2 sine theta squared, minus the inner polar curve, which is r equals 1, so 1 squared d theta. Now, in the rest of the exercise, we are going to evaluate this integral. 1 over 2, pi over 6, 5 pi over 6, 4 sine squared theta minus 1. We have again a square of a trigonometric function. So we use a trigonometric identity for that. And then we simplify this integral. So pi over 6 to 5 pi over 6. So we have, so let's see, 1 over 2 minus cosine 2 theta d theta. And the integral of that is equal to theta over 2 minus sine 2 theta over 2. Our boundaries are pi over 6 to 5 pi over 6. And when we evaluate our function at these boundaries, we find pi over 3 plus square root of 3 over 2. Hello. In this video, we are going to talk about lengths in polar coordinates. I want to start this video by directly giving you the length formula. So let r equals f of theta, where theta is between alpha and beta, be our polar curve. Now, length of r equals f theta is given by the following formula. So integral from alpha to beta of square root of r squared plus derivative of r with respect to theta squared, and we integrate this with respect to theta. Now, this will be, as I said, our formula to calculate the lengths of polar curves. But before we do an application, I would like to discuss the origins of this formula. So, let's remember that the length of a parametric curve let's say x given by g of t and y given by h of t, where t is between a and b, is given by the formula integral from a to b square root of derivative of x with respect to the parameter t squared plus derivative of y with respect to t all squared, and we integrate that with respect to t. Now, we can consider a parametric curve in the form of r of f theta as a parametric curve as follows. Polar curve r as a parametric curve as follows. So, we know the relation between the Cartesian coordinates and the polar coordinates. X is equal to r times cosine theta, and y is equal to r times sine theta. Now that we know that r is a function of theta, so we substitute in our relations r by f theta. So x becomes f theta cosine theta, and y becomes f theta sine theta. So we have now we can consider this polar curve as a parametric curve where the parameter is theta. So we now derive the quantities required in this length formula for parametric curves. So we need to find dx over d theta, so which requires us to derive this. So we have dr over d theta cosine theta plus r times negative sine theta. So we write the negative sign over here. And we also derive y with respect to theta, and we get dr over d theta sine theta plus r cosine theta. So now we, in the next step, calculate the square of these derivatives and add them. So if we square dx over d theta, we get dr over d theta squared cosine squared minus 2r dr d theta cosine theta sine theta and plus r squared sine squared theta. That's our dx d theta squared. Now plus dy over d theta squared, it's going to be dr over d theta all squared sine squared theta plus 2r dr d theta cosine theta sine theta plus r squared cosine squared theta. Now let us simplify this formula. Now, as you see, we have minus 2r dr cosine sine and plus 2r dr d theta cosine sine. So these two expressions cancel each other. Then what is left is the first terms in each sum. So, and dr over d theta squared is in common in those terms. So I factor it out. What's left is cosine squared plus sine squared times dr over d theta plus, now if we look at the last terms in each sum, we have r squared sine squared and r squared cosine squared. So r squared is in common. If we factor that out, we have r squared times cosine squared plus sine squared inside a parenthesis. Now, we use the trigonometric identity, which says that cosine squared plus sine squared is equal to 1. So, this sum of squares finally simplifies to dr over d theta all squared plus r squared. So, what we have shown in this formula or in these calculations is that dx over d theta squared plus dy over d theta squared, when our parametric curve comes from a polar curve, simplifies to integral from alpha to beta dr over d theta squared plus r squared d theta. Okay, now let's see an application of our length formula. We are going to solve the following question. We would like to find the length of the polar curve r equals square root of 1 plus sine 2 theta, where theta is between 0 and pi over 2. So, let's have a look again our length formula. We need to integrate square root of r squared plus dr over d theta. So, before I do the integration, I need to calculate the expression square root of r squared plus dr over d theta squared. So let's calculate that. First, we derive our polar curve with respect to theta. So we get 1 over 2. So we are using the chain rule. 1 plus sine 2 theta. That's the derivative of the square root. Then we derive 1 plus sine 2 theta, whose derivative is 2 times cosine 2 theta. Okay, which simplifies to cosine 2 theta over 1 plus sine 2 theta inside the square root. Then we are going to calculate the quantity r squared plus dr over d theta squared. So r squared is 1 plus sine 2 theta. So plus dr over d theta squared is cosine squared 2 theta over 1 plus sine 2 theta. Now, we try to simplify this expression as much as we can. So, first we get the common denominator, 1 plus sine 2 theta. So, we have 1 plus 2 sine 2 theta plus sine squared 2 theta plus cosine squared 2 theta. Now, in the numerator, we observe that we again have this trigonometric relation, sine squared plus cosine squared of the same argument. So that is equal to 1. So we get 2 plus 2 sine 2 theta all over 1 plus sine 2 theta. If you factor out a 2 in the numerator, you will get 2 times 1 plus sine 2 theta all over 1 plus sine 2 theta, and that simplifies to 2. So the expression inside the square root is going to be 2. So back to our length formula, L is going to be, the length of this polar curve, in other words, is going to be integral from 0 to pi over 2 of square root of 2. Okay, so this integral is square root of 2 theta from 0 to pi over 2, which is square root of 2 over 2 times pi.